No, let's go.
We're starting chapter 6. This chapter is about circles. These notes, this vocabulary, is page 182 in your textbook. The vocabulary is very important. Geometry is more vocabulary driven. I'm going to use each one of these points and then kind of interject and add to each one. The first couple ones, 1, 2, 3, 4, are pretty familiar. You should know those vocabulary terms. I'm going to hit them pretty fast. And then the other ones are new. Starting off with a circle, there's a word there, equidistant, that you need to understand. A circle is a set of points that are equidistant from the center. And what that means, equidistant, equal and distant, means that that distance there, that radius, is the same no matter how you draw it. And there's infinitely many radiuses. They're all the same. All these radiuses are the same. It never fails when I get to a problem that you have to use that people draw a blank and they don't see it right away. For example, let me go ahead and show you a problem that looks like that. We'll have a circle and we'll have a tangent and it'll look like this, and it'll say 3 and 6 and 9. Maybe that's x, like that, and they'll say find x, and people say there's not enough information, right? I don't know enough about the triangle. I got to know at least 2 sides of the triangle. If it's a right triangle, I got to know at least 2 sides of the triangle. Well, you know this distance. What is it? It's the same 6 as this 6, because both of those are radiuses and they're equidistant, then they both have to be the same. So this total length is 9, and now you could use the Pythagorean theorem to find x.
Why is that 3 there?
It's the outside, this little part here from here to here.
I was like, you're totally confusing me there.
Okay. So that's 3 and that's 6, and the total would be 9. Those both have to be 6. Why? Because they're both radiuses. Okay, so the important word there, guys, is equidistant. Equidistant. That's probably new for you, and that's the most important word in that definition. We talked about radius is a segment whose endpoints are the center and any point on the circle. A chord and diameter. Let's talk a little bit about those. A chord. Everybody understands that a diameter is a chord. Here's A, here's B, and here's C, the center. Well, that's the diameter. If it goes through the center of the circle, then it is the diameter. However, people want to say that this is not a chord, X, Y. For some reason, I don't know why, but they want to say that that's not a chord. If the endpoints are on the circle, then that's the definition of a chord. It's a chord. Okay? There might be some matching problems on the test, and it says find the chord or find the diameter. You need to know which one's which. Okay? Then that brings us to our next one, which is secant. Secant is probably brand new for you. Those of you that you heard talk about secant yet, maybe? A little bit? Alright, so here we go. Here is a chord AB. It is a segment. Notice the definition says that a chord right here is a segment. A secant, however, is a line. This is a secant. It goes through the circle and it cuts. CD is a line. Line, remember our notation, that's line CD. This is segment AB with no arrows on it. That means segment AB, and that means line CD. Okay? You with me so far? So this is a secant. A secant cuts the circle in 2 places. Okay? It can cut it like that. It can cut it like that. It can cut it right like that. The only way that a secant and a diameter can be the same thing, the way you would have to say it is that a secant contains the diameter. Here's A and B, and here's the center. If I extend that out and make that into a line, then the way you would say it is that secant contains the diameter. Okay? Because the diameter is a chord, and a chord is a segment. Okay? Diameter is a chord, and a chord is a segment. So therefore, a diameter has to be a segment. It cannot be a line. Questions on secant? Any questions on secant? Alright, that gets us to tangent. Tangent is the most important thing up here for today. Tangent, that's what the whole section is talking about. Circle tangents. Alright, So now here we have a circle. If I draw a line and it touches the circle in exactly one place, then that's a tangent. Draw this on your notes. A circle with a line that touches it in exactly one place is called a tangent. How many tangents does a circle have?
A lot.
A lot. How do we say a lot in mathematics? Infinitely many, right? Because I could draw a tangent there. I could draw a tangent here, right? As many points as a circle has, which it has infinitely many points, that's how many tangents it has. Okay? So as many points as I could come up with, that's how many tangents it has. Okay? Just one circle has infinitely many tangents. A tangent could be a ray or it could be a segment. A tangent, we call it a tangent ray, meaning it looks like this. It starts here at one point and goes out if it satisfies certain requirements. And then a tangent segment could start here and go out and stop if it satisfies certain requirements. We'll talk about that more in a second. But those, it doesn't necessarily have to be a line. It could be a ray or a segment. All right, now. Everybody got that? Now let's talk about common tangents. Not up here. Let's talk about common tangents. What does it mean, common? What if we say something has something in common?
Similarities.
All right, let's do, the first example is going to be two circles that don't touch. I think you have 4 or 5 examples. Two circles that don't touch, how many common tangents do they have? 2. Nope. There's one to kind of help you out. There's a common tangent. It touches there and there. Touches both circles one time. That makes it a common tangent.
3.
4. 4. Where would the next one be? If we got one on the top, where could we have? One on the bottom, right? There and there. So there, these are called, write this down, these are called external. Those are external common tangents. Why are they external? They're outside the circle. Those are external common tangents. Now, where would we also have some tangents? On the inside, it makes it look like a what?
X.
Like an X, right? It would come right here and touch, and go right there and touch. Not a very straight line, but you get the idea. And then right there and right there. Touching right there and right there. This would be an internal common tangent, and this would be an internal common tangent. So they might say, how many common tangents do the circles have? They might say, how many common internal tangents does it have? Or how many common external tangents does it have? And you need to know. All right, this is example A. All right, example B is going to be two circles that touch at exactly one place, like an 8, like a sideways 8, or it could be on top or bottom, but they touch exactly one place. How many common tangents would those two circles have?
3.
We'd have one on the top, one on the bottom, and then one in the middle. Are there any others? Nope, that's it. So if you got two circles that don't touch, you have 4. If you have two circles that do touch, you got 3.
Is that the internal one right there?
Which one?
That one.
This one would be internal, this would be external, and external. So we had 4 here and 3 here. All right, example C. What's another example of what two circles could look like?
Overlap.
Overlap.
How many places would they intersect?
2.
Anybody know what kind of diagram this looks like? Venn diagram intersects in 2 places. How many common tangents would you have here?
1. 3.
1, sorry. 1 that would touch right there and there. And where would the other one be? On the bottom, right there, right there. Are there any others?
No, but you can't go in the circle.
If you went inside, you would get a secant. You wouldn't get a tangent. So if the two circles overlap and they look like a Venn diagram, then how many common tangents do you have? You got 2. Where you at, Steve? What time?
Nice. 8.
You can cut it off. That's a good point.